Have you ever seen something that just doesn't make sense? Something that seems to defy the very laws of gravity. It's something you can do right now in your own kitchen with a few simple items. Imagine holding a glass completely full of water and turning that glass completely upside down. Water should go everywhere, right? What if you could flip it over and not a single drop would spill? The water stays put, held inside the glass as if by an invisible force. It's a spectacle that makes you question everything you thought you knew about how the world works. The real explanation is far more fascinating than any magic trick. It involves an invisible force that is pushing on you, me, and everything on this planet. Let's set the stage for some science. This demonstration reveals fundamental principles. Many might think surface tension is the key, but it's not. The real power comes from air pressure. This experiment helps us think like scientists. Why doesn't the water fall? Let's investigate together. We'll break down the forces step by step. The beauty of this is its simplicity. All you need is a glass, water, and cardboard. Try it yourself. Get ready to be amazed as we unpack the science. All right? It's time to roll up our sleeves and become scientists in our own homes. The best part about this experiment is that you probably have everything you need already. We are going to start with the most basic items you can find in your kitchen. First, you will need a standard, clear drinking glass with a smooth, even rim. Next is water. Simple tap water will work perfectly. You'll want to fill the glass almost completely to the top. The final piece is a piece of cardboard. A piece cut from a cereal box will do the trick. The key is that it needs to be stiff enough and large enough to completely cover the mouth of the glass. Before you begin, I highly recommend setting up your experiment space over a sink or a large tray. So, grab your glass, your water, and your cardboard, and meet me over at the sink. It's time to witness some incredible physics firsthand. Ready? Let's walk through it. First, place your glass in the sink. Carefully fill the glass with water all the way to the very top. Next, take your cardboard. Gently slide the cardboard over the top of the glass. Press down gently on the cardboard to make sure it's flat against the entire rim of the glass. Place the palm of your hand flat on top of the cardboard. In one smooth motion, turn the glass completely upside down. Slowly take your hand away from the bottom of the cardboard. The cardboard will stay stuck and the water will remain suspended inside. It's an incredible sight, isn't it? So, how did it go? If it worked, congratulations. You've performed a mind-bending science demonstration. Show it off. If it didn't work, don't worry. The seal might not have been perfect, or the cardboard flimsy. Try again with a sturdier piece and a smooth quick flip. Once you get it right, experiment. You've created a system where upward air pressure is greater than the water's downward pressure. Now get ready for the explanation. The real star of this experiment is the air, an invisible ocean surrounding us. It may seem like nothing, but air has weight and exerts pressure on everything. Imagine standing at the bottom of an ocean of air, stretching up to space, pressing down on you from all sides. This is atmospheric pressure, about 14.7 pounds per square inch at sea level. You don't feel crushed because the air inside us pushes out with equal force, creating balance. The experiment breaks this balance, making the invisible pressure visible. The atmosphere pushes up on the cardboard, easily overpowering the water's weight. That's why the water stays suspended. Air pressure wins the tug of war. Let's break down the forces at play. Pressure inside the glass pushes down, while atmospheric pressure outside pushes up. Inside, the water and a small air pocket both press down on the cardboard. The more water, the greater the downward force. But the trapped air adds a bit more. We call this total downward force P inside. Outside, the atmosphere pushes up, P outside. If P outside is greater than P inside, the cardboard stays put and the water is trapped. The experiment is designed so P outside always wins. But there's one more twist. A partial vacuum makes the seal even stronger. Here's the secret. When you flip the glass, the water sags slightly, expanding the trapped air pocket. According to Boyle's law, this expansion lowers the air pressure inside the glass. Now the pressure inside is even weaker. A partial vacuum forms. The result? The difference between outside and inside pressure grows. This pressure differential creates a net upward force, holding the cardboard tight. The vacuum sucks the cardboard up, reinforcing the seal. The water stays up not just from outside push, but from this pressure difference. It's a perfect example of physics in action. Let's recap. Team gravity, water, and trapped air pushes down, but gets weaker as the vacuum forms. Team atmosphere, our ocean of air, pushes up with overwhelming force. The upward push from the atmosphere easily beats the downward push from inside. The pressure difference seals the cardboard and suspends the water. It's not magic. It's fluid mechanics and atmospheric science. Next time you see this trick, you'll recognize the battle of pressures at play. You've turned a party trick into a lesson about the invisible power of air. This principle explains everything from drinking with a straw to how planes fly. What if you swap the sturdy cardboard for something weaker like a paper towel? The flimsy material gets wet, loses strength, and can't hold the seal. The water's weight tears through, causing a soggy mess. This failure teaches us the importance of material choice. The barrier must be strong and rigid to maintain the pressure difference. If it's too weak or porous, air leaks in and the trick fails. Experiment with different materials to see how they affect the outcome. Every failure is a chance to learn more about the physics at work. What if you tilt the glass instead of keeping it level? Tilting breaks the perfect seal, creating a weak spot at the rim. Air sneaks in, equalizing the pressure inside and outside. The partial vacuum disappears and the water crashes down. This dramatic failure shows how delicate the balance is. A smooth, level flip is crucial for success. Even a tiny opening lets air in and ruins the trick. The real secret is maintaining that airtight seal. All right, for our final test, let's get a little mischievous. We have our glass of water held perfectly upside down. The seal is strong. The cardboard is holding firm. The physics are working beautifully. Now, let's ask the ultimate question. What happens if we poke a hole in the cardboard? We are going to take a pin or a thumbtack and carefully pierce the bottom of the cardboard. Before we do it, let's make a final prediction. we are about to create a direct channel between the high pressure air outside and the low pressure system inside. What do you think the result will be? With a steady hand, you push the pin through the cardboard. At first, nothing might happen. The hole is tiny, but you have just created a pathway. Air molecules, which are incredibly small, immediately start rushing through that tiny hole. They are moving from the high pressure atmosphere into the low pressure vacuum you created inside the glass. You might even hear a faint hissing sound as the air rushes in. The air bubbles up through the water to the top of the glass, filling the vacuum. The pressure inside begins to rise, getting closer and closer to the pressure outside. As the pressure inside increases, the net upward force that was holding the water up gets weaker and weaker. The mighty atmospheric pressure on the outside is now being met with a much stronger opponent on the inside. The battle of pressures is suddenly becoming a fair fight, as the internal pressure equalizes with the external pressure. There is no longer a significant pressure difference to support the water. The only thing left holding the water back is the water's own surface, tension, and the flimsy cardboard, which is not nearly enough. The upward force from the atmosphere has been effectively neutralized. And then whoosh, in a spectacular and watery finale, the seal breaks completely and all the water rushes out. The experiment is over. By poking that one tiny hole, you proved the entire principle of our experiment. It was never the cardboard holding the water up. It was the pressure difference. Once you eliminated that difference by letting air in, the trick failed. This is the most powerful demonstration of all, because you are actively destroying the vacuum and watching the consequences in real time. It's the perfect splashy conclusion to our investigation of what can go wrong. We've seen how pressure differences can hold water. This principle appears in daily life. Think about a suction cup, like a hook. Pressing it against the surface pushes out air, creating low pressure. Atmospheric pressure pushes on the exterior, holding it in place. Lifting the edge breaks the seal, releasing the cup. Octopuses use this too. They use suckers to grip. Muscles change the sucker's shape, forcing water out. Higher water pressure clamps the sucker down. Drinking from a straw also relies on this. Sucking removes air, lowering pressure. Atmospheric pressure pushes the liquid up the straw. The atmosphere pushes it up for you. The concept of air pressure isn't just for small-scale tricks and gadgets. It's absolutely critical for modern transportation, especially when it comes to air travel. Commercial airplanes regularly fly at altitudes of 35,000 to 40,000 feet. At that height, the ocean of air above is much thinner. There are fewer air molecules, which means the atmospheric pressure is incredibly low, far too low for humans to breathe comfortably or even survive. The air pressure at that altitude is less than a quarter of what it is at sea level. This presents a massive challenge for keeping passengers and crew safe and comfortable during a flight. To solve this problem, engineers have designed airplanes to be, in essence, giant, high-tech flying cats. The main body of the plane, the fuselage, is a sealed pressure vessel. Powerful systems on board pump air into the cabin, artificially increasing the pressure inside to a safe and comfortable level. This is what we call cabin pressurization. The systems maintain a cabin pressure equivalent to being at an altitude of about 6,000 to 8,000 feet, which is a level our bodies can easily handle. This creates a massive pressure difference between the air inside the cabin pushing out and the very thin air outside pushing in. The plane's structure must be incredibly strong to withstand this constant outward force. Have you ever felt your ears pop during takeoff or landing? That sensation is your body's direct experience with changing air pressure. As the plane climbs, the cabin pressure is gradually lowered from the ground level pressure to its cruising altitude pressure. The higher pressure air trapped in your middle ear needs to escape, so it pushes on your eardrum until it pops through the eustachian tube into your throat. The reverse happens during landing. As the plane descends, cabin pressure increases, and you need to let higher pressure air from your throat back into your middle ear to equalize the pressure, which is why swallowing or yawning helps. This massive pressure difference is also why airplane windows are so small and thick, and why the airplane door is a marvel of engineering. The door is a plug door, meaning it's shaped to be slightly larger than its frame on the inside. When the cabin is pressurized, the pressure difference itself forces the door into its frame, creating an incredibly strong and perfect seal. It's physically impossible to open the door mid-flight because you would have to fight against thousands of pounds of air pressure pushing it shut. This application of pressure physics is a silent, life-saving hero on every single flight you take. Atmospheric pressure is key in meteorology. A barometer measures this pressure. Mercury barometers use a mercury column to balance atmospheric pressure. High pressure means clear skies, while low pressure often brings storms. Pressure differences create wind, flowing from high to low, helping forecasters predict the weather. This experiment demonstrates Pascal's principle, discovered by Blaise Pascal. It states that pressure applied to a fluid in a container is transmitted equally throughout. The atmosphere is a fluid enclosed by Earth's gravity. The weight of the air creates pressure in all directions. This principle powers hydraulic systems like car brakes and hydraulic lifts. Our experiment shows how atmospheric pressure pushes up, counteracting gravity. You've seen Pascal's principle in action, a real force you can harness. In science, we love to put numbers on things. It helps us be precise. Scientists measure atmospheric pressure using a unit called a Pascal, but we usually talk in terms of kilopascals. At sea level, the standard atmospheric pressure is 101.2 kilopascals. That's equivalent to about 14.7 pounds of force on every single square inch. So the next time you see a weather report that mentions barometric pressure, you'll have a better sense of what those numbers mean. You can connect those numbers directly back to the force that held the water in your upside down glass. Today, we journeyed into the heart of a classic science experiment that seems to bend the rules of reality. We started with a simple, almost unbelievable sight. A glass of water turned completely upside down, yet refusing to spill. It looked like magic, but as we've discovered together, the explanation is far more wondrous than any illusion. The secret lies not in a trick, but in an invisible and immensely powerful force that surrounds us every moment of our lives. Atmospheric pressure. This vast ocean of air we live in is constantly pushing on us. And this experiment simply made that invisible push visible in the most dramatic way possible. We learned that this isn't just a simple case of one force pushing up. It's a beautiful interplay of several physical principles working in perfect harmony. We saw how the weight of the water inside the glass, combined with the pressure of a tiny pocket of trapped air, pushes down. But we also uncovered the secret weapon. As the water sags ever so slightly, it creates a partial vacuum, lowering the pressure inside the glass even further. This action creates a significant pressure differential, a clear imbalance between the weak downward push from inside and the mighty upward push of the atmosphere from the outside. This pressure difference is the true hero of our story. It's what keeps the flimsy piece of cardboard sealed tightly against the rim of the glass, holding back the water against the pull of gravity. We then explored the limits of this principle, discovering that a weak card, a tilted glass, or a tiny pinhole is all it takes to break the seal, equalize the pressure, and bring the experiment to a watery end. These failures weren't setbacks. They were crucial lessons that reinforced our understanding of how the delicate balance of pressure works. They proved that the vacuum seal is the key to success. From this single elegant demonstration in our kitchen, we were able to connect to a universe of real-world applications. We saw the same physics at work in the powerful grip of a suction cup, the life-sustaining environment of an airplane cabin, and the complex art of weather forecasting. What began as a simple trick with water and cardboard became a gateway to understanding the fundamental forces that govern our world. You have not just learned a trick, you have gained a deeper appreciation for the unseen physics that shape your everyday experience. Now that you have become an expert on the science of air pressure, the journey of discovery doesn't have to end here. A true scientist never stops asking what if. So, I have a challenge for you. We performed our experiment using a glass with a rigid rim and a piece of sturdy cardboard. But what if we change one of those key variables? Your mission, should you choose to accept it, is to try this experiment again. But this time, use a flexible plastic cup instead of a rigid glass one. How do you think this change will affect the outcome? Before you begin, make a hypothesis. Think about how a flexible cup might behave differently from a rigid glass. When you grip the plastic cup to flip it over, might you accidentally squeeze it? What would squeezing the cup do to the shape of the rim and the integrity of the seal you are trying to create? Consider the forces at play. Will the atmospheric pressure still be able to hold the cardboard in place if the rim itself can bend and warp? This is your chance to think like a physicist and predict the result based on what you have learned about pressure and structural stability. Once you have your prediction, it's time to experiment. Grab a plastic cup, fill it to the brim, cover it with cardboard, and give it a flip over the sink. Observe carefully what happens. Did it work as well as the glass? Did it fail immediately? Did you have to hold it differently to make it work? The results you get will provide you with new data and new insights into the conditions required for this demonstration to succeed. This simple variation on our experiment opens up a whole new set of questions and deepens your understanding even further. Don't stop there. Science is all about curiosity. What happens if you use a larger container, like a bucket, or a much smaller one, like a test tube? What about using different liquids, like salt, water, or oil? Each change you make is a new experiment waiting to be performed. Keep exploring, keep questioning, and keep putting science into your own hands. The world is full of amazing phenomena, just waiting to be understood. Thank you for joining me on this incredible scientific adventure. Now go out there and keep experimenting.